Hey, good morning, everyone. Great to have you here for day 2 of our 3-day extreme heat workshop. Really excited to have the chance to make a couple very brief opening remarks and reflections today before getting to our opening speaker, which I'm really excited about. So one thing I was thinking about sort of on the way over is, and sort of reflecting on some of the first workshops we did on extreme events at Columbia, say 5 years ago or more, is I think sort of the emergence of this understanding that heat is highly nonlinear. I think there was sort of a feeling, at least among some climate scientists several years ago, that heat and high temperatures was sort of the well-behaved climate variable. And I mean, I think that's changed so much in the last few years that it's hard even to come up with statistics to describe all that we're observing in the extreme heat space, in the impact space, right? Just to grab one example we've heard about a little bit already, more than 1,000 people dying during the Hajj, just this last year. But it's too many examples to even mention. And another way to think about it is the extent to which heat is really emerging in this dialogue relative to other threats and hazards that haven't decreased at all. Things like sea level rise and coastal flooding, right? Those threats are as great as ever. But increasingly, heat is moving centrally into this narrative, as is these multivariate hazards, heat and sort of sea level rise together, for example. So I just wanted to take a second to sort of unpack these notions of this nonlinearity and its implications a little bit, right? Because what we're talking about with extreme heat and its impacts is the stacking of nonlinearities on top of each other, all right? And the challenges that poses. So let's unpack some of those nonlinearities into the changes in average temperature that we're observing, which is the highly nonlinear relationship between the statistics of extreme heat and those average temperatures, as sort of a second component. And then a third component, impacts and vulnerability to a given amount of extreme heat, right? All of these things are highly nonlinear. And then when we bring in the compound dimension too, how heat interacts with other variables like coastal flooding, how our sectors that we've thought about individually interact in this cascading impact space, and we start to see what these challenges are, right? So just like super quickly, global average temperature, right? If you look at the last 125 years of global average temperature and sort of stack years so that on the y-axis you have temperature anomalies in the global average per year, basically what you see is the warmest years have been the recent years. But if you're stacking 120 years together, the departures between any of those individual years, their anomalies on the y-axis, are tiny, right? You're putting 120 years into basically a 1.5 degree Celsius anomaly or so, right? So essentially 0.01, 0.02 degrees tends to separate those individual years until we get to the last 12 months, right? Then suddenly we have a situation where pick any of those last 12 months, they've typically been as much as about 0.3 degrees, right? Warmer than any of those other 120 years, right? So we have to be open to, and we can talk about whether the extent to which El Nino is responsible for that versus global warming itself. But this last year has been a huge departure from any departures we ever saw before, averaged across the whole year. So that points at possible nonlinearities in the first case. Then we get to the relationship between the statistics of our extreme heat and that global average temperature. And here we saw all these talks yesterday about how we're seeing these unprecedented magnitudes of extreme heat, unprecedented persistence, unprecedented spatial extent, right? It's making it hard to even define these events. And then we're also hearing about, as we go to the impact space, how each additional amount of warming of a heat wave or duration of a heat wave produces these powerful nonlinearities. Our bodies aren't adapted for that little bit of extra heat. Our energy systems aren't adapted to that little bit of extra heat. The risks of productivity loss, major health impacts, death, power failures precisely at those times when we can't afford to be having the power go out are all increasing in these nonlinear ways, right? But it's not just single sector impacts, it's the interaction, the probability of multiple climate hazards occurring in sequence at the same time, also increasing dramatically, and the impacts are totally impossible to quantify, arguably. So one of the challenges of our time is How do we still try to make quantitative projections? They're still useful, but we're facing deep uncertainties here, right? But there are known things, right? Things that we can count on. The statistics are shifting. The most vulnerable populations are going to continue to be most centrally at risk, and we need narratives around solutions. Ultimately, the nonlinearity of solutions is the thing, if anything, that's going to save us. And that's really the pivot that I wanted to make to our speaker this morning, because I think you can see some signs that in the solution space, there are some powerful nonlinearities starting to work in our favor. Most of them, I think, are in the emissions reduction space. I think one of the challenges for us as the community thinking about heat is where do we see in the adaptation space those signs of traction, of new technology, of upkeep, of thinking about the vulnerable. And I think we're not yet meeting that challenge of showing a nonlinear positive story about resilience to heat. There are individual stories out there, but we need more uptake. And one of the most powerful ways to do it, of course, is through communication, right? We are ultimately a social species, and so we need to lean into those leaders who have devoted their careers to pointing out the vulnerabilities, especially of those communities we don't hear enough about, and telling those positive stories about the solution space, about empowerment, so that people can have narratives and really believe in positive solutions. And with that, I'd like to pivot to a quick bio for someone we're thrilled and so lucky to have speak to us this morning, Somini Sengupta from the New York Times. She has been a reporter with the New York Times for over 20 years. She's major international coverage. She's led the bureaus in Western Africa and across South Asia. She's reported from over 50 countries, including 10 conflict zones. She's written a book. Wouldn't want me to spend any time talking about all the awards she's received, so I'll just maybe bookend a couple from the beginning and towards the end of her career. The George Polk Award for International for Reporting back in 2003. And then in 2023, recently, co-award on the National Press Award for newsletters for her work at the New York Times, which has really pivoted in the last 5 years to being sort of the central figure, I would probably reporting among the major reporting at the Times on climate, which points to these kind of powerful levers and is so essential towards that tipping point where solutions can keep up with the challenges I articulated. So thrilled to have you here, Somini. Thank you for giving us some remarks today.
Hi, good morning, everyone. Can you hear me? Is this all right? All right. It's absurd that I'm here this early in the morning. I may not make very much sense. And it's absurd that an underqualified person such as myself is speaking to a room full of academics. So thank you. I was going to read to you from the top of a story that I wrote now 4 years ago, so it feels a little dated. But I just want to open with this scene, and it's from Stockton, California, from August of 2020. Work began in the dark. At 4 a.m., Briseida Flores could make out a fire burning in the distance. Floodlights illuminated the fields, and shoulder to shoulder with dozens of others, Miss Flores pushed into the rows of corn. Swiftly, they plucked, one after the other, first under the lights, then by the first rays of daylight. By 10:30 a.m., it was unbearably hot. Hundreds of wildfires were burning to the north, and so much smoke was settling into the San Joaquin Valley that the local air pollution agency issued a health alert. Miss Flores, 19 years old, who had joined her mother in the fields after her dad lost his job in the early days of the pandemic, found it hard to breathe in between the tightly planted rows. Her jeans were soaked with sweat. It felt like 100 degrees in there, Miss Flores said. We said, we don't want to go in anymore. She went home, exhausted, and slept for an hour. All this work to harvest those dried, ochre-colored ears of corn meant to decorate the autumn table. I I read to you from this story because it's helped me learn, I think, 3 things about extreme heat. One, extreme heat is how millions, billions of us today feel climate change on our skins. 2, extreme heat is not only felt unequally by people like Briseida Flores who have to work outdoors, but it kind of lifts the lid. It reveals the underlying inequities in our society that were there. And because of that, I think adaptation to extreme heat means very different things in different places and requires creative and quick thinking because it's a problem of now. So just last week, I think, I wrote about a few of these adaptation measures. Some were very obviously heat oriented. So I wrote about farm worker groups who've been advocating for many years for heat protection laws at the state level. Washington, California, Oregon, 5 states around the country right now have very minimal protections for outdoor workers. But again, I emphasize they are minimal because they don't really address the underlying challenges. Many of these workers, farm workers, for example, may not have access to health care. So they may have lots of underlying health issues that exacerbate health risks during heat. They live in homes, mobile home parks, for example, that trap heat. Some get paid by how much they harvest, right? Or how many garments they stitch in a garment factory. So there's a structural disincentive to take breaks, to take rest breaks. So these are issues that are not really heat centered so much, but they have everything to do with how to reduce human suffering in extreme heat. Another one of the sort of heat solutions that I wrote about was a very simple app, a location services app that was created by a scientist, by a climate scientist in Greece, and it shows you, it's a location services app, so it shows you in your city where are there cooling centers, swimming pools, shaded parks, but it also shows you the coolest way, the coolest route from point A to point B. And if you're particularly vulnerable, it shows you the coolest route with rest stops along the way. Extremely useful. I've used this, but it's only available in 4 cities in Europe. These functionalities have not been baked into the maps that most of us use, even though we could use it. And then the third solution that I learned about when I was reporting this story is about a very creative new insurance tool that pays out when temperatures hit a certain threshold. It's a parametric insurance model. Temperatures hit a certain threshold, and workers who have bought that insurance product get a payout. Now, that too has lots of limitations. It's still very small. The poorest can't afford market rates for insurance, so this one is almost entirely donor funded. It's been rolled out this year for the first time to 50,000 women in India, informal sector women who have no social safety net at all. So, it worked this year for those 50,000 women who got the payouts, not because it was a new product on the market. It worked because it was offered to them by an organization that these women trusted, that they had worked with for decades. This organization had helped them set up bank accounts, had helped them when they fell on hard times. So what I learned from this was not just the cleverness of an insurance tool, but the importance of community trust and credibility in promoting some of these heat solutions. So what I would love to learn from you and from your research in the coming months and years is what kinds of measures are being tried out, what kinds of measures are working, not just hardware things like reflective paint, which we've written about, increasing shade trees in cities, which we've written about, but what other kinds of, for lack of a better word, software? What other kinds of hacks, whether they're zoning laws, workplace safety laws, community building, violence prevention, what are some of those other things that are being tried out, that are working? So not just things that can help protect people, but how people can care for each other and protect each other in times of extreme heat. So I look forward to learning from you. Thank you.
Thank you so much, Somini. That's great, and we're thrilled to have you with us today. So I think with that, we'll jump right into our first session of the day. This is our second and final session focused on the physical drivers of extreme heat and projections. And to get us started, I'll turn it over to James, who's chairing the session. Thank you. Thanks again, Somini.
Hi, everyone. I'm James Doss-Gollin from Rice University in Houston. Welcome to this session on, let me make sure I don't butcher this, on the physical drivers and projections. To get started is Colin Raymond from UCLA. To all of the speakers, Colin, as you come up here, you're gonna get a warning when there's 3 minutes left, so that's a good time to start wrapping up, and then you'll get a final warning with 1 minute left. If you're done by then, we'll have time for questions. Otherwise, we'll move on quickly. So with that, Colin.
Thanks, everybody. This will be a tough act to follow, I think. But I will do my best to hopefully convince you of the relevance of two recent projects. One is underway, actually, and one was recently published with some collaborators who are in the room and others. Let's see if I can operate this properly. Okay, so very briefly, the motivation for both studies is that the little icons represent storms on the left and extreme heat on the right. And of course, both of those can contain multiple hazards, heavy precipitation, of course, for storms, as well as winds, other things like hail. And then, of course, extreme heat can be high temperatures as well as, for example, humidity. And those can have impacts on hard infrastructure, on health directly, for example, through hospitalizations or lost wages, and then kind of indirectly through things like power outages. And the question then is, are these hazards actually correlated? Not just, is there a chance of them happening near each other, but is that chance greater than random? And if so, how and where? So we might a priori expect, and I'll focus on humid heat. As some of you know, that's my bread and butter. And we might expect a connection. We might expect a positive correlation, that is, because, well, a few different physical reasons, let's say. But there might also not necessarily be a connection. For example, if the drivers are quite distinct, so high temperature and humidity maybe have an offsetting effect, or maybe things are quite local, such that there's not necessarily a sort of organized connection in any meaningful way. So the first case was recently published about atmospheric rivers and humid heat. So very briefly, the main points of this are that we just defined from a reanalysis humid heat days, and then we focused on peak humid heat days. So we were focusing on the drivers that tend to amplify humid heat rather than sustain it. And then we defined atmospheric rivers with a standard database. So atmospheric rivers are usually thought of as large organized corridors of high moisture. So this database looks back at reanalysis and defines that for the whole world at 6-hourly resolution. And then we have quite a strict definition of the interaction between the two. So we only consider the two hazards to interact if they occurred at a certain point, if they occurred within 1 day and 100 kilometers of each other, so comparing different grid cells. And then we look at the regions from the US National Climate Assessment. So this is, I guess, the most important figure from that paper. So this is showing relative to chance, and given a humid heat day at a given location, what is the probability of also having an atmospheric river, again, within 24 hours and 100 kilometers. So you can see there's a few different things going on here. I'll focus on the northern, so there's both positive and negative sort of interactions or probabilities. And I guess I should note, ARs aren't perfect, so they don't really capture the North American monsoon that well, so that's kind of what's going on the southwest. But if you focus across the northern tier of the country, sort of from Montana to Maine, you can see that the chance of an AR near a humid heat day is maybe 2 times higher than it would be expected randomly. And a side note, this is all defined during the warm season, of course, and while ARs are usually publicized as sort of a winter West Coast phenomenon, they actually account for about half of the extreme precipitation in the warm season east of the Rocky Mountains. So moving on, without too much delay, this is just a composite timeline for each of the regions, showing that the ARs tend to happen just after the peak, around the time or just after the peak of the humid heat. So that's a bit similar to Casey's result for Rio de Janeiro yesterday. And then just briefly kind of stepping through what this actually looks like, sort of the day before peak humid heat event, and then the day of and the day after. So on the day of, there's sort of a bit to look at, but if you look at the left, you can see there's humid heat in the shading, and then sort of a broad area of elevated risk of atmospheric river. And then on the next day, everything's kind of shifting. This is defined for the Midwest, so it's sort of centered. The humid heat is now centered on southern Wisconsin or so. And then there's an atmospheric river. And if you look at the right side and the hatched shading, that sort of is showing where the axis of the atmospheric river is hitting. So they're very close together, actually, with the atmospheric river just a tiny bit behind the peak humid heat. And then the whole thing kind of starts to shift into the northeast on the next day. And that's all composite. So, of course, individual cases can differ quite a bit. And then this one, hopefully this is not too complex to convey. So what we then decided to do is, well, maybe this is sort of explained by geopotential height. Geopotential height is sort of correlated with the total temperature and moisture in a column. So it is, of course, closely related with heat waves. So the question then is, are atmospheric rivers and humid heat related just because maybe atmospheric rivers occur when the geopotential heights are higher? But actually, if you normalize by that, you can still see that for a given geopotential height, the larger, more widespread atmospheric rivers are connected with significantly more likely humid heat. Okay, so I've already hit these points, and I don't have too much time, so I will move along, but I guess I will point out the effect of atmospheric rivers on humid heat is stronger than the connection between humid heat and precip or humid heat and vapor transport alone. So there's an important role, we think, of spatial organization, essentially, in controlling this compound hazard. Okay, so now to some preliminary work on tropical cyclones and humid heat. So, of course, doesn't really need too much motivation about why both of these hazards are important. And if you look just at a map globally of where these things occur, they tend to occur in some of the same regions. So similar to what I said before, are they dynamically connected, or is there just a risk of one happening after the other by chance? So we've been starting to look at that, and then a further point of motivation, I suppose, is that this is a current brochure as of a few months ago from the Louisiana Department of Health, and they note that one of the best ways to prevent heat-related illness is air conditioning. But of course, Louisiana is a state with high risk of both of these things, so it's a bit ironic that they point this out when loss of air conditioning is a major risk in that location. So we define tropical cyclones with the standard sort of definition from the global database. We define just another measure of humid heat, essentially, from reanalysis. And then we have another fairly strict definition of interaction. So in this case, we're defining the interaction, or one occurring near the other, if they happen within 24 hours and 500 kilometers And we only even look at hurricane strength tropical cyclones, so it's quite a strong requirement here. So you can think of it as basically conditioned on a tropical cyclone being nearby, what is the relative risk of humid heat? So again, I guess I'll hit the punchline and then back it up a little bit. So this graph is from is only through 2017, but I think the point still stands. And as you can see at the top, this is the all-time maximum humid heat at a given location. And that covers quite a significant part of the global oceans, actually, meeting this definition. And you can actually even see individual storms that caused the record humid heat in different parts of the ocean. And there's a big maroon blob near Hawaii that I'll get to in a second. And this is a paper from a few years ago of mine, where you can actually see, you can ignore the white there, but the red box actually shows you can see those tracks on this map. We didn't really notice it at the time. So it's a good case of, I guess, looking back at your own or others' work. And furthermore, if you look at a particular storm, you can actually see how, again, this is the all-time record humid heat at the shaded grid cells here was caused by Igor and occurred on the days of the year as Igor's track moved through the North Atlantic. So it really is a direct connection, and you can see that for some other storms. This is just a sample from 2010 also. And you can actually we can do even better than that, which is if we zoom in, now we're looking at Bermuda, and just looking at the precip field and the moist static energy, so another humid heat measure at a snapshot. This is a certain hour, or maybe it's a daily average. In any case, on September 19th, you can see that near Bermuda, the precip field is just to the south. Moist static energy, high humid heat is to the south. And then I guess this is the next day. The storm, of course, has moved past Bermuda, and the humid heat is progressing along with it. And this was verified by looking at the Bermuda Weather Service report. And Bermuda actually has really good narrative summaries of the weather, so this is very nice. You can see in the box there, they point out the closest point of approach was 40 nautical miles to the west at midnight, and that was actually the exact hour that the highest moist static energy was observed at the main Bermuda airport weather station. So essentially simultaneous with the passage of the tropical cyclone center. So just to go back to the global view then for, I suppose, the remainder of the talk. This is just a table of the storms that have caused the largest spatial extent of this all-time record humid heat near them. And you can see a few storms. So that moon blob near Hawaii was partly caused by the storm Oho in October 2015. A couple other Hawaii area storms are on here too. And just for reference, California is about 0.45 million square kilometers. So that's about the size of these things. Also, the Black Sea is about this size. And now I've shaded the ones that are during El Nino years. So there's clearly a very strong connection here. And then just looking at land only, unfortunately, some of these global maps don't really include small islands that well. So, islands aren't really well represented, but you can see a couple places of interest here. And then you can see that on the map here, the two Australian representatives. And then we can do the same kind of trick that we did for Bermuda, which is plotting the exact map of the precip and the storm and the moist static energy, humid heat, and everything just kind of goes along together. All right, so I guess I'll skip okay, maybe I'll show this other map as the last one. All right, so this is showing the relative risk of, this is now 95th percentile humidity at a given location, and this is still preliminary work, so we're not sure the reason yet for the negative relative risks, but in most of the global subtropical ocean, there's a positive risk, and we're trying to look at some of the composites. I guess the point here is that the moist static energy maximum, if you look at like the bottom row, is actually quite close to the storm center, which is essentially what we saw for Bermuda, but is pretty widespread over, 1,000 kilometers or something. And then if you look at a time series, you can again see that the risk goes up and down over the time span of a few days. So we're still trying to understand, I guess, the relative roles of temperature and moisture anomalies, adiabatic, radiative, diabatic processes and all of this, but certainly the connection is quite compelling. El Nino seems to play a major part of it. And so in general, yeah, I guess the main things to take away are humid heat is not just a fair weather phenomenon. It can occur when there's clouds around, even quite close to precipitation events. And so looking at these things on a sort of sub-daily scale and trying to understand the processes, we think is important for continued progress on these important hazards. Thank you.
Thank you, Colin. We're at time, so we're going to move on, but please catch Colin with your questions at the break. Next, we have Zhang from NYU, who's going to present.
Thanks everyone for coming, especially many thanks to the organizers. My name is Zhang, and I am an assistant professor at NYU Courant Institute for Mathematical Sciences. So I'm going to start with a phenomenon that everyone is familiar with. This is just boiling water in a pot. And the water is heated from the bottom, and warmer water rises and colder water sinks. So this phenomenon is called convection. And the same phenomenon also occurs all the time during a heat wave, where the land surface is super hot and it's trying to get rid of the heat by either heating up the air near the surface or by evaporating water into the air near the surface. So what convection does to the stratification of the water is that it makes sure the buoyancy of the fluid at the bottom is always less than or equal to the fluid at the top. So the column is always slightly either stable or only slightly unstable. And for water, it means that the temperature at the bottom is less than or equal to the temperature at the top. And for the atmosphere, it means that the moist static energy at the bottom does not exceed the moist static energy, the saturation moist static energy at the top. And moist static energy is a fundamental variable in atmospheric dynamics. It's a combination of three terms: temperature, humidity, and height. As an air parcel rises from the surface to the top of the troposphere, the temperature would decrease, and the water vapor inside the air parcel is going to condense. But if you look at the moist static energy profile, it's roughly conserved, and that's why we use it, and it's very convenient. So, as I said, convection during a heat wave will always cap the moist static energy near the surface. So even we have a very strong anticyclone in the upper layer, and it makes the free tropospheric temperature super warm, the surface temperature is bounded. And we can derive this bound by using just a few steps of reasoning. I'm not going into the details here, just want to point out two things. One is that the right-hand side, which is a free tropospheric term, only depends on the temperature in the free troposphere. And for the left-hand side, we let the humidity to go to zero, the surface humidity to go to zero to allow the surface temperature to go to its maximum. So then we arrive at an upper bound for the surface temperature that contains a few terms, but essentially it just depends on the temperature in the free troposphere, T500 here alone. So this is what the upper bound looks like when it's plotted. The y-axis is surface temperature plus an offset from the surface elevation. It's considered known. And the x-axis is the free tropospheric temperature, and it depends on the large-scale circulation, whether there's an anticyclone or a cyclone over this place. So we have this simple theory, and we are going to test it against observations. And we're going to plot the distribution of observations on this plot. And The good thing is that the observations do support this theory, that the distribution just lie right beneath the upper bound, and very few data points exceed the upper bound. The upper bound is not linear. So at very low T500, the slope is smaller, and at higher T500, the slope can double. And that is mainly because the water vapor content in the atmosphere goes nonlinearly with temperature. And this nonlinearity does have consequence. So, for example, let's take a look at the Pacific Northwest heat wave that got brought up multiple times yesterday. So this event, highlighted by this red dot here, broke the previous record, highlighted by the blue dot here, by a huge margin of 5 degrees Celsius. And it actually makes sense when it's plotted in this space. So we are comparing two extreme heat events. So the baseline T500 is pretty high, and the slope is above 2. And we had a T500 anomaly of about 2 Kelvin between these two events. And this number gets immediately doubled at the surface to about 5 Kelvin. And you can also see that this data point is still quite a bit away from the upper bound. So that means if the surface was drier, this event could be hotter. And the upper bound connects the surface temperature to the free tropospheric temperature. And you might be wondering, what determines the free tropospheric temperature? So unfortunately, there's no simple answer for the mid-latitude atmosphere. But for the tropics, we do have an answer. So for the tropics, we have that when there's deep convection, the MSE over land is coupled to the MSE in the free troposphere, and the same thing works for the ocean. And what is special about the tropical atmosphere is that the free troposphere is roughly uniform in temperature. So you can consider the free troposphere as a uniform lid that caps the maximum moist static energy everywhere, either over land or over ocean. So these two moist static energies are coupled, and because moist static energy is a function of temperature and humidity, and what is that? That is just heat stress. So the wet bulb temperature, by definition, so it's a metric for heat stress. By definition, it's tightly related to moist static energy. So based on this dynamics, we expect that the changes in the extreme wet bulb temperature over tropical land should be roughly equal to the changes in the warmest portions of sea surface temperatures in the tropics. And we plotted the 2 time series here, and you can see that these two are highly correlated, very similar. So the land, TW max over land is averaged over all land regions. And the SST is the warmest 25% of monthly SST. So in order to predict the extreme wet bulb temperature over land, we just need to predict the sea surface temperature. And the first thing we notice is that there is an upward trend, and that's because of the global warming signal. And there's also a lot of interannual variability, and it's because of the ENSO variability. So I highlighted all the El Niño peaks, and following each El Niño peak, there is a peak in the wet bulb temperature extremes and in sea surface temperature. So this lag between the peak El Niño and peak tropical free troposphere is actually noticed in many prior literature in atmospheric dynamics, but it's not discussed in the context of extreme heat. So we combine these two pieces of information together, and we build a prediction model for any maximum wet bulb temperature over land for the upcoming year based on 2 things. One is the linear warming trend. The other is the ENSO variability, which we use the December ENSO index in preceding years. So this model captures 80% of variance of TW max over land in the past 4 decades. If you run a hindcast, so we fit the model in time with all the data prior to a certain year and predict this year, and we get these prediction intervals. The actual wet bulb temperature extremes have been falling within these prediction intervals. So the last one is a prediction for 2024, but we are only halfway through. And this year is actually special because we just had a strong El Nino event by the end of year 2023. And we want to have a rough estimate of the effect of this strong El Nino on extreme heat stress in 2024. So we can do that, not super rigorously, but we can have a rough estimate using the regression coefficients from this model. And we found that the effect of this strong El Nino on extreme tropical wet bulb temperatures for this year is roughly equivalent to the past 20 years of global warming, which is quite substantial. We can also estimate the chance of a record-breaking annual maximum wet bulb temperature over tropical land. Of course, this probability will depend on the strength of the El Nino. So if we were in a neutral state in 2023, the chance is close to 0. But because we had a very strong to very strong El Nino, this chance rises to 68%. So that's all the results I have. So we explored the convective constraints on heat extremes, and we derived some general rules for mid-latitude extreme temperature and tropical extreme wet bulb temperature. And given the audience here, I'd like to say that I'm interested in extending this work into the adaptation and solution space, and I'm curious what ideas you might have. Thanks.
Excellent. We have time for a couple questions, so please either come forward or is someone, Deepti, can you keep an eye out for anything online? Someone check for online. Yep.
Thank you. This is a very interesting, very impressive fact to be able to link the physical process to very useful information about this extreme. So I would like to ask you about, so you talked about the tropics where you know about the upper level temperature, but what about the mid-latitude? So do you think that in the future we might get some upper bound that might be relevant also for mid-latitude?
As I said, mid-latitude is more complicated. So I don't know. For the mid-latitude right now, we only have the vertical connection, but I don't know what the tropospheric temperature will be like.
Hi. Thanks for the talk. So the convection constraints that you calculated were using Eulerian methods. I was wondering if you see the same constraints in a Lagrangian method, if you check that, if you saw convection when actually tracking air parcels or not.
I think there is somebody else did this recently after my paper came out.
Mm-hmm. And he didn't see convection?
I don't know.
Okay. Thanks.
Thank you. It's really glad to see if we can use like El Nino index to predict in the tropics, but it's still like good news. I'm wondering if the reason why do you use like December El Nino index for the annual TW?
So we fit the model with all the months, with ENSO index from all the months. And actually, if you start from June, you get a pretty good prediction skill. It's similar to using December. But we use December because that's usually where the strength of the ENSO, the El Nino, is maximum.
Thank you.
Wonderful. Up next, we have Rachel White from University of British Columbia.
Okay, thanks, James, and thanks for the organizing committee for inviting me to speak today. And so I want to talk a little bit about connections between atmospheric waves and heat waves. And I want to credit my fantastic group that I have up at UBC and these students who have all contributed to some of this work. And so I'm going to come back. I'm from the University of British Columbia, so I'm going to come back to a heat wave that we've heard a little bit about over the last couple of days, which is the Pacific Northwest heat wave of June 2021. And so here is the sort of atmospheric circulation preceding the heat wave. And so this is this geopotential height that we've heard a little bit about. But essentially what we need to know is that these regions of positive geopotential height anomaly give high pressure in the atmosphere, and they, for various reasons, lead to increases in heat at the surface. And so this was just before the heat wave, and here it is during the heat wave itself. And so we've got a really strong region of this high pressure over the Pacific Northwest region that leads to these extreme temperatures. And we've heard a little bit about these extreme temperatures, but this is just a plot from sort of an overview paper that we published last year, where we looked at by how much were previous records broken, and this is all time records, not just day of year records, at different regions. And so the shading is from Era 5 reanalysis back to, I think it was 1950 at the point that we published this. And then the dots here are observational stations, some of them going back to about the 1880s. And so you can see that records were broken by sort of 4, 5, even up to 6 degrees Celsius. And so this was a really extreme event. And for context, here are a couple of other heat waves that we've heard a little bit about over these sessions. We've got the 2003 European heat wave and the 2010 Russian heat wave. And so you can see in terms of the amount by which records were broken, this Pacific Northwest heat wave was incredibly extreme. Now, I'm sort of interested a little bit in okay, well, we know this region of high pressure caused the heat wave. That was the atmospheric circulation that led to this heat event. And Matthias Roslersberger and Lucas Papritz have done this really nice study looking at, well, what exactly is it? What brought that heat into that region? And usually there's sort of 3 things that we think about. And so there's advection. And so are we moving air from a region that is hotter, usually further towards the equator, into this region and therefore bringing in hot air? And so that's this one over on the left. What they show is actually that didn't really contribute that much to this event. And then there's 2 other pieces that really come with these systems of high pressure, these geopotential height anomalies that we expect to see. And so one is called adiabatic warming, or it's just sort of subsidence, and so it's air moving downwards in the atmosphere. And what that actually leads to is warming of the near surface temperatures. And then we also have, and so that's this one, that's this one in the middle. And then we also have what's known as diabatic heating. And so it's sort of direct heating of the atmosphere and surface. And so that might be from radiation. And so in particular, in these regions of high pressure, what we see usually is really clear skies because we have this subsidence. Any clouds evaporate and you get clear skies. And so you have a lot of solar radiation. You can also get diabatic heating from things like latent heat in upstream atmospheric rivers, and a number of studies have sort of looked into how some of those things played a role in this heat wave. But I was particularly interested in, in this heat wave, we can see that diabatic heating, this direct heating, played an important role. And so it's sort of interesting to me that this heat wave really did occur sort of just after the summer solstice. And so in terms of the solar radiation that was coming into this region, we had basically the maximum at that point that this region could have. So here is the solstice. This blue line is just showing incoming solar radiation for this particular region over the Pacific Northwest. And here was the 2021 heat wave. And so I was just interested in terms of, we've had a lot of studies on the Pacific Northwest heat wave in terms of, what was the role of sort of drier soils? What were some of the roles of the feedbacks between the dry soils and the atmospheric circulation? But I was just interested in, well, what is the role of the fact that this almost happened on solstice? And so we know that this radiation plays a role within these sort of high-pressure systems leading to heat waves, but how much of a role? And so essentially I was interested in, well, what happened if the heat wave had happened with the solar radiation of 30 days later, or even 60 days later? And so to answer this question, we essentially just ran a regional climate model. And so Tim Shui at the UBC ran the WRF, Weather Research and Forecasting Model, for us over this particular region. And so the boundary conditions, the weather conditions are pretty much identical. So we've got the same initial conditions, we've got the same boundary conditions in each of our simulations. But all we do is basically just trick the model into thinking that it is later in the year, and so the model has a different solar radiation. And so here's an example. We've sort of got one heat wave we're calling sort of the June heat wave is our control simulation. The heat wave happened at the time of year that it actually happened. And then we've got a couple of others. Here we've shown sort of this August, and so this is 60 days later. And so you can see we've got quite a big difference in the solar radiation coming into this region. Not only is the peak radiation higher in June, but also that radiation starts earlier in the day and finishes later as we've got earlier sunrises and later sunsets. And so then we sort of analyze these simulations to look at, well, how much of this is the temperature different between these different simulations? And so here again, this is basically the figure that I was showing before, where it's like, okay, these were the records that were broken when this heat wave occurred in June. And so we just look at the differences in the model between our sort of June control simulation and our 30 days later simulation, look at the differences in the maximum temperatures that we reached at each grid point, and then sort of use the observational records broken to say, estimate, well, by how much would records have been broken if this heat wave had occurred with the solar radiation of 30 days later? And so that's this plot here. And so you can see, okay, records were still broken over a large region, but it is less severe, and the differences are sort of around about 2 degrees Celsius over this region. And then this is 60 days later, so towards the end of August. And so here we see, okay, there's a really big difference here in terms of how much records would have been broken. And so this is just sort of quantifying the effect of this near solstice solar radiation. It's not actually saying, well, if this heat wave had happened in August, it would have been this much colder, because there are a lot of other things that would have changed. The sea surface temperatures would have been different, and I think importantly, soil moisture would probably have been drier, and that would be counteracting this impact. But it is interesting for me to see, well, actually this solar radiation and this seasonal cyclone solar radiation can actually play a pretty big role and sort of comparable to soil moisture differences in this particular event. And it is worth also noticing that depending on where you are in latitude, obviously the role of solar radiation is going to be different. Okay, so I now want to sort of shift onto a slightly different project and come back to these, this atmospheric wave. And so, as I said, we've got these waves of geopotential height. So we've got this really strong anomaly here. That's the high pressure that's causing this heat wave. But this is sort of part of this broader wave in the atmospheric circulation. It's not just an isolated region here. You can see particularly here, we've got these negative and then positive and then negative. These are these atmospheric waves that we're interested in understanding, well, how might these be changing with climate change? Because these are the circulation patterns that lead to some of these strong extreme heat anomalies. And so I'm not going to expect you to sort of follow necessarily the slide unless you're really in this field of atmospheric dynamics, but just to give you a sense of how many different ways we currently have to estimate atmospheric waviness. And so this is just sort of going back to 2014. We've got Fourier amplitudes, there's a meridional wave amplitude, a meridional circulation index, local finite wave activity on potential vorticity, local finite wave activity on geopotential heights, geometry of PV contours, sinuosity of the Z500, wave packets of now you're looking at meridional winds, average latitudinal displacement of PV. We've got all of these metrics to try to say, well, how do we characterize, how do we quantify atmospheric waviness? And it turns out it actually does matter which one of those we pick. And so even back in 2013, Screen and Simmons said that the links between Arctic warming and wave amplitude are sensitive to the definition of wave, of how we define this atmospheric waviness. And this is a nice study by Ruth Geen and co-authors who, in some idealized simulations, looked at, okay, how do waves respond to Arctic amplification? And so along the x-axis here, we have sort of Arctic amplification with a warmer pole. And then along the y-axis, we've got wave amplitude. And so we're just going to focus on the blue lines. The different colors are different ways of defining Arctic amplification. But just for the sake of this one, I've highlighted these blue ones with some lines. So this is one metric of wave amplitude. And so you can see with Arctic amplification in the blue, there isn't that much change in the waviness of the atmosphere. But if you define waviness by a different metric, you see that there's a really strong increase with Arctic amplification. And if you use two other metrics, some of them show increases, one of them shows a strong decrease. And so it really matters which metric of atmospheric waviness we're using when we're trying to understand how is this going to change into the future and how will that impact surface extremes. And so the question that we're asking in my group is like, well, which of these waviness metrics are most closely associated with surface extremes? And we're using a similar sort of probability ratio of just saying, well, what's the change in the probability of extreme temperature when we have high waviness? And so we've got this sort of probability of an extreme happening when you have waviness relative to the climatological probability of an extreme. And so here's just a show of various different metrics. And so we've got 5 of these, this array of metrics that we've shown. And you can see in general, for summer heat waves, yes, high values of waviness are associated with an increase in the probability of extremes. So that's a probability ratio greater than 1. But if we look in particular regions, you can actually see, well, it's quite different depending on where you are. And so it does matter which one of these you're using. And some of them are more strongly connected to extremes than others. And so in particular, we saw this local wave activity anticyclonic basically picking up on geopotential height anomalies. And so this is currently under revision, and one of the reviewers very, interestingly pointed out, well, can't we just look at geopotential height anomalies? And so we just did that. And actually show, well, actually, maybe we don't need complex metrics of atmospheric waviness. Maybe we just need to look at anomalies in this geopotential height metric. Now, there are some complications in terms of trends in the geopotential height and those pieces that we'd need to sort of figure out. But I think that's an interesting piece for me to be thinking about of like, oh, do we need to go to all of this effort? And then the last thing I just want to show is trends in this. And so now I'm looking at trends in these geopotential height anomalies of like exceeding a certain value. Here we have an era 5 and the CSM ensemble mean. And so what we're seeing is, yes, there are trends in the observations, but they don't necessarily match what we're seeing in the large ensembles. And in this particular model, if you look at individual ensemble members, we do see actually you can get a lot of different trends just by looking into an individual ensemble member. And sort of you can say that this one is actually quite similar potentially to what we've seen in observations, which is suggesting that maybe a lot of what we're seeing in observations could be internal variability. But that would also mean that we'd have to really trust the models are doing the right thing with atmospheric dynamics. And so this is complicated, but I think this is sort of interesting to think about what's happening here. And the last thing I want to point out is within the CESM, we can look at these single forcing experiments. And so we can try and isolate different anthropogenic forcings. And here on the top is the trends in the CESM with greenhouse gases of this sort of geopotential height anomalies. On the bottom is that's from anthropogenic aerosols. And so you can see that in the CESM, at least, these are really going against each other and might be contributing to why there's so much uncertainty in how these metrics might be changing, because we'd have to really trust our model's representation of the aerosols and their impacts on the dynamics. And so future work will really look into whether other models are doing similar things. Thank you. I will leave up my conclusions.
All right, again, we're unfortunately out of time for questions, but again, I encourage you to follow up with those in the break. So next we have, you think you remember things and then things leave your brain. Next we have Yinglin Tian from Potsdam.
Hi everyone, I'm Yinglin Tian. I'm now a postdoc in Potsdam Institute for Climate Impact Research in Germany, working with Kai Kohlhuber. It's a really huge pleasure to participate in this wonderful workshop. And because I recently defended my PhD thesis and just recently joined PEAK as a postdoc, so today I will present some of my PhD work and some of our ongoing research in PEAK. So from yesterday and to today, the previous oral and the postdoc presenters has already told wonderful stories about why we want to focus on heatwave days, because they have impact on home health, they will influence food production as well as plant carbon sequestration compatibility. And this is then very important for us to understand what is going on when we have heat waves. So, as E has already mentioned, this figure, this review figure, they have already summarized several very important procedures during heat wave days. For example, when we have the blocking, we will have more incoming solar radiation, and that will heat surface. At the same time, the blocking will also favor the L substance that will bring in the adiabatic heating. And then once the soil moisture is dried out, it will decrease the latent heat flux that will further increase the sensible heat flux and further intensify temperature anomaly. And apart from that, warm advection can also contribute to temperature anomaly. And then here is the work that is mentioned by Rachel. So in this work, they try to decompose temperature anomaly into these three components. And later on, based on these three components, they try to classify the heat waves in the global scale into different categories. However, if we go back to this research, we can see that in this equation, they cannot well distinguish the role of solar radiation or latent flux or sensible flux because they present all kinds of adiabatic heating in one term. And this is the motivation or the starting point of the work that I will present followingly. So in our work, we first try to further decompose the adiabatic heating based on surface energy balance. And in this way, we will have 7 major energy contributors instead of 3 contributors. And then once we have these 7 energy contributors, we can further classify the heat waves in the global scale. And then we pick up 1 representative heat wave types to further quantify the interaction between the compounding drivers. And here we use expandable machine learning method. Based on that, we hope to explain the occurrence of record-breaking heat wave days or extremes. So to decompose the adiabatic heating further, we use surface energy balance. So surface energy balance tells us that these 5 components, the sum of them should be 0. And then one of them, upward long wave radiation, can be written as a function of skin temperature. And then by differentiation this equation, we can further decompose the skin temperature into the contribution of these 5 components. And further, there are already several research that state that the adiabatic heating actually is very closely related to the change in skin temperature. And in this way, we can represent the surface L temperature anomaly into these 7 components. And then after having this framework, we use ER5 reanalysis data to do the analysis. So we only focus on the summer season, but for tropics, we use the all-year data, and we also just focus on the three-dimensional heat waves, which cover a certain region which has least duration of 5 days. And in this way, we will have 800-something heatwave events, which include this certain amount of heatwave days. And then for each of heatwave day, we decompose the temperature anomaly into these 7 components. Then we use this components array as a feature to further classify the heatwave days using k-means as a method. And to decide the number of clustering, we use CO2 index. And here you can see that this index peaks at 4, which tells us that in our case, it is best to cluster the heatwave days into 4 categories. And today, because of the time limitation, I will just focus on one kind of heatwave days, which is sunny, dry heatwave day. But I'm really pleased to discuss more about other types during the coffee break if you are interested. So here you can see that for this kind of heatwave days, it majorly has 2 energy contributors. One is the increased solar radiation, another one is decreased evaporation. And if we look at the distribution, we can find that so this type of heatwave days, they are not located at an area which is extremely dry, but it is the location is relatively dry. And if we further look at the correlation between temperature anomaly and soil moisture anomaly, we can see that this category actually is located at an area which has higher this correlation. So this can further justify our clustering. And then we use the 3 variables to further investigate the mechanism of this sunny dry heatwave days. So not surprisingly, it has high pressure, but not that high as other category. And consequently, it has low cloud cover. And again, it is not the strongest decrease in cloud cover. But what makes this category stand out is that it has strongest soil moisture. And in our manuscript, we also further look at impact of 4 categories of the ecology and human health. But here I will not go to the details. And then we look at the difference in the frequency of sunny dry heatwave days between these 2 periods. And we can find that it has a widespread increase in global. And compared to other categories, actually it has most widespread increase in the global scale. And around 50% of that area even will experience 2 times more increase of this category. So it is very important to further look at this type. And here comes our ongoing research in peak. So we have already know that for this category of heat wave, it actually has 2 major energy contributors, which can further be linked to geopotential height and soil moisture. And here we want to ask one more question, which is how the interaction between this compounding driver will contribute to the temperature anomaly. And this is inspired by the very nice work led by Samuel Bartosek. To do this, we first pick up the Europe as a representative region. And what we do is that we use machine learning method to decompose the temperature anomaly into these 3 components: the direct contribution of the atmospheric driver, the direct contribution of soil moisture, and the contribution of the interaction between these 2 compounding drivers. And then following that, we are trying to explain the occurrence of record-breaking heatwave days. So this is our method. What we do is that we use the potential height anomaly and soil moisture anomaly as input to predict air temperature as an output. And what we use is gradient boosting regressor currently. But as we know that our machine learning method is more like a black box. We do not know what is going on exactly inside the black box. And this is how explainable machine learning method come to play a role. So here we use shape value, which can quantify the contribution of different contributor of the machine learning method, as well as the interaction contribution of different contributors. So in our case, it would be direct contribution of geopotential height, direct contribution of soil moisture, and interaction. And then after we have this quantification, we calculate the relative contribution of these three components, and then we plot the contribution along with temperature anomaly, and we want to look at how they will change with temperature anomaly, especially at the upper tail of temperature. So this is the very preliminary result with France regional main data. Here are the here are the procedures, how I produce these plots, but I will not go to details. And again, I'm very pleased to discuss more during the coffee break if you are interested. So I will jump to the plot that I get out of it. The y-axis are the relative contribution of these three components to temperature anomaly, and the x-axis, we can understand it as the temperature anomaly. So we can find that actually these three components, they more or less they have a nonlinear regression with temperature anomaly. Especially we find this plot is really appealing to us because we can find that before temperature anomaly arrive around 2.5 Kelvin, actually the contribution of interaction, it does not contribute a lot to temperature anomaly. Only after this critical changing point, it starts to increasingly contribute to temperature anomaly. And further, we also want to quantify this nonlinear behavior in the global scale. So here we choose two metrics to describe this nonlinear behavior. One is the difference between R square of the nonlinear fitting and the linear fitting. And this metric can tell us how nonlinear this curve is. And the second one would be the R square of the second piece, or the upper tail part of the nonlinear fitting. And here is the map for the global scale. We can say that by the first metric, we can say that generally the interaction contribution will show more nonlinear regression with temperature anomaly, especially over the middle latitude region. And then to look at R square, so the R square of the upper tail actually both direct and interactive contribution. They have a high value, but they are located at different locations. And here we want to further describe this different distribution with a metric. So here we choose aridity index and the correlation coefficient between the potential height anomaly and soil moisture anomaly. So we can find that over very dry region, actually the direct contribution, they will show some nonlinear regression with temperature anomaly. But over the semi-dry or semi-humid region, we can observe more strong nonlinear regression between interaction and temperature anomaly. And further, we can look at that the locations with higher correlation coefficient between the potential height and soil moisture. Here, we can see better upper tail correlation between interaction and temperature anomaly, which again can support our outcome based on machine learning method. So here is our summary, and to move forward, we will try to repeat this analysis with model data to say whether the model can also reproduce this nonlinear regression, and we also look into plan to look at this relationship using ensemble boosting data, because now with reanalysis data, the data sample is limited at the upper tail. Okay, so that's all. I'm pleased to answer any questions.
We do have time for a quick question. Can you double check online? Great.
Thank you.
Okay, wonderful. Next up, we have Mingyu Park from Princeton.
Hi everyone, my name is Mingyu Park and I'm a postdoctoral researcher in Princeton University. So in this talk, I'll present some results on the role of moisture transport in the development of North American summertime heat waves in climate model simulations. So I'd like to start this talk with the 2021 record-breaking Pacific Northwest heat wave case again. Another way to visualize this event is by using the CPC daily maximum temperature as shown here. So the color shading here is the 5-day average of the daily maximum temperature highlighted over the Pacific Northwest region. And we see that in panel C, the red shading is concentrated over the region, indicating that temperature on average exceeds 40 degrees Celsius or 104 Fahrenheit. And some recent studies suggested an important role of extratropical diabatic heating that amplify this rich or anticyclonic circulation over the Pacific Northwest. So in the upper left panel, this is a snapshot of outgoing long-wave radiation before the occurrence of the heat wave. And we see this indicates extratropical cyclone structure with the water vapor, which is also captured by this column integrated water plot. We see clearly signal over the North Pacific Ocean. And these studies noted that this latent heat release from this extra water vapor and moisture result in the amplification of the downstream reach over the Pacific Northwest region, as represented by the two different circulation metrics in the bottom panels. And other studies further linked this anomalous moisture transport to the atmospheric river activity. I think in the earlier talk, Dr. Raymond already gave a nice summary of this atmospheric river. And another way to visualize this atmospheric river is looking at the integrated vapor transport field itself. So the figure here depicts the snapshots of integrated moisture transport before the Pacific Northwest heat wave again. Each panel represents the different date preceding legs. And we see this narrow, elongated, filament-like structure over the North Pacific Ocean, often termed as atmospheric river, representing intense moisture transport driven by atmospheric circulation. So these studies noted that atmospheric river is also linked to the Pacific Northwest heat wave. And previous studies further suggested that this large-scale atmospheric circulation anomaly is related to this atmospheric river activity. So we see this negative dashed lines and solid lines recurrent over the North Pacific Ocean. We often termed it as a wave train. This is depicted by also 500 hectopascal geopotential height anomaly. So these studies emphasize that this wave train drives this, serves as an important precursor of this Pacific Northwest heat wave, and they further trace this source of wave train to back to the East Asian monsooner heating. So this is a schematic diagram of physical processes associated with mid-latitude summer heat waves. So we already have seen this twice already, really highlighting that this is our best knowledge of physical processes. And so there are multiple physical processes interacting each other, which is described in further detail in this domain scenario 2023. We can roughly separate these physical processes based on the medium of these processes in the upper atmosphere and the near surface. If we focus on the upper atmosphere part, different from the two previous studies showed this schematic diagram, we can see all the processes that I mentioned earlier are illustrated. From low speed wave train to the moist ascending airstream or moisture transport to the atmospheric blocking or persistent anticyclonic circulation system. And the studies that I introduced before are all based on the 2021 Pacific Northwest case study. So the questions naturally follow are, can we generalize this relationship? And also, secondly, does climate model simulate this contribution of moist process? To address these research questions, for observational data, we use a CPC maximum temperature, daily maximum temperature data set again. We analyzed 1979 to 2023, 45 boreal summers, 0.25 degree, roughly 30 kilometer horizontal resolution. And for meteorology, we use ER5 reanalysis, which is commonly used in climate science. And for climate model output, we use a sphere large ensemble developed by NOAA GFDL. This is a suite of coupled climate model simulations, aims to analyze long-term climate change and also the related physical mechanisms. It has a 50-kilometer resolution for atmospheric and land components. Is pretty high from the standard of climate model data, and has 1 degree for sea ice and ocean. And also, it has 30 ensemble members, basically representing 30 different Earth-like climates simulated by models. For methodology, we adapted the definition of persistent heat extremes. So for daily maximum temperature data, I will skip the details, but we basically applied 2 different statistical techniques and then identified persistent heat extremes. And so based on this definition, we can count the occurrence of heat extremes over North America. And we can see that there are some regional hotspots. For clearer visualization, if we subtract this 40 north to 60 north average value at each grid point, and we can clearly see that the Pacific Northwest region and the Central North America have really anomalous heat extreme days over the 45 summertime. And then, so as denoted by these 2 shades in this figure, in this study we defined 2 different domains, Western North America and Great Plains or Central North America. And now I define heat extreme event as when certain percentage of the area of the domain undergoes heat extremes. And for the results I will show in the next few slides, lag 0 corresponds to the onset day of this event. And the model sphere similarly captures these regional hotspots, surprisingly. Okay, jumping into the results, this is the observational result for the Western North America. We identified 49 events, the shading over this, the green shade here. And if we look at the onset day, consistent with the definition, we see this high daily maximum temperature anomalies. And what's interesting here is the green contours representing this intense moisture transport anomalies. We can see that since lag -2, this moisture plume reaches Alaska and the upstream region of a heat wave. And these results may remind some of you that it is similar to what we have seen for the 2021 Pacific Northwest case, as depicted by here. And this heat wave event accompanied atmospheric blocking. So do we see such feature? And I think yes, the answer is yes. If we overlay the 500 hectopascal geopotential anomalies again, we see there's a strong evolution of this field representing atmospheric blocking indeed plays a role in this heat wave events. And if we look at the farther preceding lags, we see this black contour, the repeating this ridge trough ridge pattern actually is observed since lag -7. So what it means, what it implies is that it is really a preceding Rossby wave train that plays a role driving this moisture transport and the subsequent atmospheric blocking. And then Western North America heat waves. Okay, shifting our gear to the Great Plains case, what's interesting here is that even inland heat waves and the onset day, it also accompanies this green contours upstream of the heat wave domain, indicating that the moisture transport indeed precedes these inland heat waves as well. Yeah. And if we overlay this geopotential height field again, then the sequence of physical processes that I mentioned earlier, Rossby wave train to moisture transport to the subsequent atmosphere blocking or anticyclonic circulation system also can be observed nicely in this composite plot. What about climate model? So does climate model simulate this sequence? And I want to argue that the answer is yes. So the left column shows the Western North America heatwave cases, and the right panel shows the gray plain cases. And we indeed see that the upstream moisture transport occurs for both wave event composites in this climate model simulation. Yeah. And if we can visualize this more clearly from the heatwave centered plot. So the left column now shows the 3 panels. The first panel is the daily maximum temperature anomalies. So the white dot is located at the center of the heat wave, the peak of the daily maximum temperature. And the x-axis is the longitude, and y-axis is the latitude based on this center. And the second and third plot represent the integrated vapor transport or the moisture transport and the atmospheric river frequency respectively. And we can see that there is a clear signal that upstream moisture transport indeed occurs with respect to these heat wave cases. And more than 30% of these heat waves accompany atmospheric river. If you look at the circulation fields as well, then the geopotential height anomaly indicate there's an anticyclonic circulation system overlaid. And if you track the atmosphere blocking frequency, more than 50% of heat waves accompany or entail atmosphere blocking therein. And the spear also, what's nice about the spear is it also captures those characteristics of Western North America heat waves. Not only the daily maximum temperature anomaly itself, the spatial extent and magnitude, but also for the moisture transport processes with the spatial pattern and the atmospheric river frequency located upstream of the heat waves. And then if you further look at the circulation map, even atmospheric blocking frequency is well captured by the climate model simulation. Again, they also simulate that more than 50 or near 50% of heat waves accompany atmospheric blocking. And for the interest of time, I'll skip the Great Plains case in detail, but basically the point is the upstream moisture transport also is clearly seen from this centered heat wave centered plot for these inland heat waves cases. And SPEAR also tends to capture these key features, although it overestimates a bit of this daily maximum temperature anomalies and underestimates moist transport processes. Okay, to wrap up, I want to point out that this upper level circulation processes from Rossby wave train to moisture transport and the subsequently amplifying reach or blocking is generally holds for both coastal and inland heat waves, which is well reproduced by climate model simulations, in this case, GFDR SPEAR model. But I did not cover the importance of surface processes in this talk, but the contribution of surface processes is also considerable, but also regionally dependent. And the model used in this study tends to overestimate this contribution, particularly for the Great Plains heat waves cases. And before I finish, I want to advertise that Su-Chin Juan from UCLA and myself are co-convening the extreme weather session in the upcoming AGU meeting. We welcome any heat-related research in this session, so if you are interested, please feel free to reach out to us. And the session number is A054. Yeah, thank you for your listening.
Thank you. We again have time for a quick question, if there's one from the audience.
Hey, Mingyu, that was a really nice talk. I have a question about when you were showing the biases in the Great Plains, you were saying that it overestimated temperature.
Yeah.
And I think you were showing that the moisture transport was underestimated. Do you think those two are linked?
Yeah, I think so. The way I interpret this is the moist process related contribution to the atmospheric blocking or anti-cyclonic circulation is relatively weak, but still we have overestimated daily maximum temperature anomalies. So some not upper atmosphere related processes contributed that warming, and I interpreted it as a surface processes driven.
So like it's maybe not dry enough or something?
Yes, kind of biases over this domain.
Cool. Thank you.
Yep, thanks.
Great. Next up, we have Donghyuck Yoon, also from Princeton.
Hello everyone, I'm Donghyuck Yoon, also from Princeton, and I'd like to switch gear from atmosphere to land surface process in this time. So our research mainly focuses on the understanding how different land-atmosphere coupling behavior in the previous 2022 CONUS compound drought and heat wave events, and we also explore the implications of these different coupling behavior for forecasting the medium range forecast in the GFTL shield model. Right, so as many of you already know, drought or soil moisture deficit condition over certain region can intensify the heat wave condition. But in terms of this downward process, heat wave can also play a significant role in the development of drought condition. So if we take a look at the physical mechanism behind for these compound drought and heat wave events, so for example, some soil moisture deficit or decreased soil moisture can reduces the evapotranspiration and eventually increases the surface air temperature over the same region. And if we look at this downward process in turn, this increased surface air temperature or heat wave condition can increases the evapotranspiration and eventually decreases the soil moisture or accelerate the development of drought condition. So we can easily find the two different coupling behaviors in terms of the evapotranspiration for these compound drought and heat wave events. So first is soil moisture and evapotranspiration coupling, described as blue color. Another is temperature and evapotranspiration coupling, also described as red color. So there can be two kinds of coupling behaviors for evapotranspiration during compound drought and heat wave events. So let's see the detailed process for these two different couplings. So first is soil moisture and evapotranspiration coupling. From a very previous approach, if soil moisture is within certain range called wilting and critical points, then the evapotranspiration or evaporative fraction is linearly limited the amount of soil moisture content over surface. So this process can be considered as the water or soil moisture limited process or water limited regime. So we can say that the drought condition can be increased as a decrease of soil moisture and evapotranspiration in the water limited regime. In contrast, if soil moisture exceeds the critical soil moisture, then evapotranspiration becomes independent of the amount of soil moisture. It could be also considered as energy limited condition or energy limited regime. Then what can control the evapotranspiration under this energy limited condition? The answer is atmosphere. So under the energy-limited condition, evapotranspiration is mostly controlled by potential evapotranspiration. For example, according to the previous study by Pendergrass et al., evapotranspiration increases as potential evapotranspiration increase under energy-limited condition. Simultaneously, soil moisture rapidly decreases as moisture evaporates from the surface to the atmosphere due to the high atmospheric demand or potential evapotranspiration. So this process also can be considered as flash drought. So the potential evapotranspiration can be simply defined as the source of the atmosphere, and it is a function of net radiation, wind speed, vapor pressure deficit, and surface air temperature. So we can regard that temperature can be coupled to the evapotranspiration under this energy-limited condition. So we now know there are two kinds of coupling behaviors for compound drought and heat wave events, especially in terms of the evapotranspiration. So simply, under the water-limited condition or dry regime, soil moisture or drought condition mainly contributed to the development of heat wave through this process. In contrast, in the wet regime, atmospheric condition or heat temperature mainly controls the drought condition. So we mainly investigated the following two questions throughout this study. So first one is, can these two different behaviors be observed the previous compound drought heat wave events? If yes, can this behavior affect to our model's predictability? So we firstly defined the heat wave and drought days based on the percentile criteria. I skip the detailed process, and we eventually detected major three regions which experienced severe compound drought and heat wave events during the 2022 July and August. And they are named as Northwest, Great Plains, and Northeast by their longitudinal positions. So as you can see, all of these three regions experienced extremely dry and hot conditions during our target period, but their temporal variation during the analysis period were different. So we further assessed their time series or temporal variation of development of these compound drought and heat wave events. So as I mentioned before, the coupling behaviors for compound drought and heat wave events can be observed by examining the evapotranspiration. So we further assess the time series for maximum temperature, soil moisture, and evapotranspiration averaged over the three regions during our target period. So firstly, you can confirm that soil moisture and evapotranspiration had a strong positive correlation in the Northwest and the Great Plains during our target period, and these characteristics was more prominent in the Great Plains, with a significant negative correlation between temperature and evapotranspiration or soil moisture. In contrast, in the Northeast, soil moisture didn't have a large positive correlation to the evapotranspiration. Instead, there was a significant positive correlation between temperature and the evapotranspiration in the Northeast. Even we can also find some positive anomaly of evapotranspiration during some pentat with rapid decline of soil moisture. So we can assume that there can be two different coupling behaviors in the Northwest and Great Plains and Northeast. So we further assess these two different kind of coupling, the impact of couplings on the predictability for our GFDL model. So I'd like to briefly introduce the GFDL shield model designed for forecasting the short-term to medium-range time scale for the multi-spatial scale extreme events. So there are various configurations for our model, but in this study, we utilized these global 13-kilometer configurations, which is initialized on 00 UTC for a 10-day forecast. So let's see the predictability of this shield model for previous compound drought and heat wave events. So I'd like to check my. Okay. All right. So left figure shows the time series for soil moisture and temperature over the Great Plains. So black lines indicate the in-situ observation result, and orange-colored line shows the forecast result from the 10 different lead time of the shield model. So the darker orange color indicate the longer forecast lead time. So as you can see, even if shield didn't largely underestimate the soil moisture, in other words, shield doesn't have a large dry bias, there was a strong overestimation of heat wave at the same time. So then what can cause this overestimation of temperature of Great Plains? So we further assess the same feature for latent heat flux and sensible heat flux, and we firstly found that there was a similar temporal pattern between soil moisture and latent heat flux, which indicate that coupling behavior between soil moisture and latent heat flux, even in the model result. And notably, there was a overestimation of sensible heat flux, which can induce the overestimation of surface air temperature. So this result indicates that the soil moisture independent factor may relate it to the overestimation of sensible heat flux and eventually the warm bias. So we further assess the factor to drive the overestimation of sensible heat flux for the Great Plains. So these figures shows the spatial patterns for bias of temperature and sensible heat flux over the Great Plains of the 10-day forecast lead. So you can find there are similar spatial pattern between temperature and sensible heat flux bias, and again, there was no significant dry soil moisture bias. So these kinds of overestimation of sensible heat flux can be also driven by the error in the net solar radiation bias. So I'll skip the detailed explanation about this process, but I'd like to emphasize that the surface radiation fluxes or land surface condition also play a critical role in the predicting heat wave over the water-limited region like this Great Plains area. So let's move on to the northeast. So similar to the Great Plains result, we also assess the temporal variation of soil moisture and temperature for our shield model, and we can find that there was a perturbed variation of soil moisture and temperature by comparing to the Great Plains region. So we further assess the relationship between this temporal error between soil moisture and temperature in the northeast. So as you can see, during this pentad, which demonstrates strong energy-limited process during the compound drought and heat wave events, shield model even predicted the increase of soil moisture rather than the development of the drought observed in the observed. And at the same time, we can also find the significant underestimation of surface air temperature. So we further assess the relationship between these errors in the shield model by plotting the trend from during these pentas. So for example, this green colored arrow shows the regression lines during these two pentas for soil moisture, and similarly, this magenta arrow line indicate the regression line for temperature. So as longer forecast lead time, as you can find that the slope of regression line varies. So we further record this variation of slope in the below figure, and we found that there was a significant correlation between these two regression lines. And more interestingly, we found that the slope for the other potential evapotranspiration related variables, such as vapor pressure deficit or wind speed, also has very similar trend with the soil moisture or temperature. So this result implies that potential evapotranspiration related variables mainly controls the soil moisture predictability during this pentad on the northeast. So as summary, we now know that there were two distinct coupling behaviors for compound drought and heatwave events in the 2022, and we also found that they can affect the medium-range model forecast predictability. Yep, that's all. Thank you.
All right, again, please catch up with Donghyuck in the coffee break. Next up, we have Elon Vakrat from the University of Toronto.
Well, hi everyone. Today I'm going to present my current work on heat waves and blocking and some insights we got on how they will change in the future using methods from dynamical systems. As this is the 7th technical talk you're hearing today, I thought I'll change the title to something more clickbaity, so maybe now I'll catch your attention. Okay, so on today's agenda, I'm going to give a short brief on the mechanisms of heat waves, and then I'm going to move to how our method that we used and how it is different than prior works. We're going to talk about persistent days dynamics, both in reanalysis data and in global climate models, and how it will change in the future. And we're going to lastly answer on if all models agree, and if not, then why. Okay, so you heard that before. Heat waves are projected to increase in frequency, in duration, and in intensity by the end of the century. But this increase can come from either a thermodynamic mechanism, or how the energy balance in the atmosphere will change, or a dynamic one, a change in the atmospheric circulation. So we're going to focus on how the dynamic mechanism will change, if it will change. So dynamically in the European summer, it is controlled by these low and high pressure systems that move around and interact with the mean flow or the jet. But from time to time, there's this high pressure system that stays in the same place for over a week or so and can create a heat wave. So if this is our domain, the European summer, and this is the mean flow, this large high pressure system stays in the same place with a clear sky condition, and a high solar flux can create a heat wave. So let's see how it plays out. What you see here is a composite of all the heat wave days we found in our reanalysis data, and this is a discomfort index heat waves, meaning the average between the temperature, the regular temperature, and the wet bulb temperature, so we can catch that humidity effect on humans' health. So in figure A, this is the discomfort index anomaly. Unsurprisingly, it is high across all the continent. And what we also see is this high pressure system that go from ground level to the middle of the atmosphere that comes with a negative zonal wind anomaly. So this is connected to the picture we saw before. So this is good, this makes sense, and we can move forward. And we want to ask the question on how these anti-cyclonic systems will change in the future. So, of course, we are not the first one to ask this question, but the problem is that works with different blocking indexes, or how they found this high-pressure system, and different global climate models gave different results. So, yeah, that's the problem. And what we're going to do different is instead of looking for these blocks, we're gonna calculate the persistence for each individual day. So we don't know if it has some sort of a high pressure system, but we're gonna look for for days with a high persistent value. And what you need to know is that days with high persistent values is days that consecutive days after it looks the same. So intuitively, blocking structures, as it is a persistent mechanism by definition, we would expect them to have a high persistent value, but we don't know that. We're gonna do the same calculation for each day. So what we see here on the left is what you saw before. These are heat wave days. And what you see on the right is the high persistent days, the days that have the most persistent values. And although there are two independent analyses, there is a high match between the two groups of days. So they both have high discomfort index anomaly and a high pressure system with negative zonal wind anomaly. Moreover, for heat wave days, the median value of the persistence is almost at the 90th percentile of the whole persistent distribution. So we want to connect that to the fact that we know that blocking is a persistent mechanism and heat waves are created by blocking. So there should be a match between the two groups. So this is good, this works in reanalysis. And now we're going to move over to global climate models. So this is the mean picture for 19 different climate models for the most persistent days. And what we see is a very similar picture dynamically and a high discomfort index anomaly, which is a bit lower than the reanalysis anomaly, but still it is positive. We connect that negative difference to the fact that the wet bulb temperature doesn't really react well in global climate models. Okay, so this was in the historic runs, and now we want to go into the future, as we know this method works. So this is the whole persistent distribution, the historic distribution, and in red what you see is the persistent distribution by the end of the century under the higher anthropogenic emission forcing. So the dots are the median value of persistence, and the dashed lines is the 90th percentile, and we see that positive shift in the distribution. So what can we learn from it? First, we're going to talk about the most persistent days in the future. And dynamically, we don't see a big difference in the anomaly in comparison to the historic runs. But what different is how large is the discomfort index anomaly in the most persistent days in the future. And we connect that to the fact that we know that heat waves are becoming more intense by the end of the century. So going back to this distribution, maybe because there are higher persistent values by the end of the century, it will mean that the blocking duration will increase. But what we see here, so the dashed dot lines are the historic runs, and the dashed lines are the end of the century runs. What we see is to the onset and after the onset, the slope of the anomaly is the same, meaning that the total duration of the events doesn't change. Okay, so maybe the frequency will change, maybe because what used to be the 90th percentile is now in the 70th percentile, meaning a threefold increase by the end of the century. But again, the answer to this question is no, and we see that. So each row is a different decile, and these are the three different scenarios we checked. And the anomaly stays the same across different deciles. So even if the 8th decile has a higher persistent value than the 9th decile in the historic runs, the anomaly is higher in the 9th decile in the historic runs. Meaning what important is the absolute theta value in comparison to the total distribution. So again, we don't see an increase in the number of anomalous days. Okay, so once again, going back to this distribution, what hides is the fact that this is a mean of 19 different models. So there is a discrepancy between different climate models, and it goes from 1% of increase in persistence to 20% of increase in persistence, when the mean is 12%. So we want to understand why is there a discrepancy between different models. So to answer that, we looked at the temperature change and the equator to pole temperature gradient and how it will change in the future. So each dot is a different model with colors are the same across all different figures. And what we see here is that as the mean temperature increases and the equator to pole temperature gradient is reduced by the end of the century, the more increase in persistence the mid-tropospheric flow becomes. So again, there is a correlation between the temperature distribution and value and the increase in persistence. So lastly, to conclude, 5 major conclusions are: first, theta -1 can be used as a proxy variable for blocking events, both in reanalysis data and in global climate models. We saw that greenhouse forcing will increase the persistence of the mid-tropospheric flow by the end of the century, and it will amplify heat wave. But we saw that the increase in frequency and duration of heat waves is coming from a thermodynamic mechanism and not a dynamic one. And lastly, we saw that the change in the persistence of the mid-tropospheric flow is coming from the change in the temperature and the reduction in the equator to pole temperature gradient. So thank you for listening, and I'll be happy to answer any questions.
Are there any questions?
Hey, thanks. Very interesting. So, do you interpret this to mean then that your persistence metric is not a metric of blocking?
So, it is a metric of blocking. We saw that there is a high match between persistent days and high pressure systems. So, it is a good variable for blocking, but it doesn't mean the frequency or the duration of the block will change, if this makes sense.
It's very exciting. I mean, the trends that you showed, there were trends in persistence.
Yep.
But I think you also showed that there wasn't a trend in the frequency or duration of blocking.
Right. So although the mid-tropospheric is becoming more persistent, it doesn't mean that the duration of the block will go up, because a block is an interaction between the mean flow and small-scale anticyclones and cyclones. So we will also see a decrease in them, in the intensity of them in the summer. So these are two canceling effects. This is what we think.
Cool.
So the total duration of the block will not change, because these are two canceling effects.
Great, thanks.
Hi, Elon. Yeah, thanks for this really nice talk and great study. I was really impressed by the reduction of zonal winds in the mid-latitudes that you clearly showed there, that is associated with these blocking patterns. And to me, it does look a lot, also because there seems to be an increase in very high latitude winds there in that anomaly plot, that there might be some type of double jet pattern present, and like connecting this to your other result that the equator to pole temperature gradient might play a role in this whole story. What is your idea of how these two things could possibly be connected?
Okay, so I didn't think about that. What I did think is that, going back, we see that the mean flow is going around it. So this negative anomaly is here, but there is a positive anomaly in the pole, so it's just a flow that goes around this pressure system. So I don't know if it answers your question, but I didn't see a connection to, or I didn't think about a connection to the reduction in temperature gradient.
And finally, we have TC Chakraborty from PNNL.
Hello, everyone. So I'll be talking about measuring and modeling physiologically relevant urban heat. And I'm going to start with something that most people already know here, that the urban heat island effect, where cities tend to be warmer than their surroundings, which has relevance for potential for additional heat exposure within cities. Because of the heterogeneity of cities, you get a lot of spatial heterogeneity in the local urban warming. Here, for instance, you see an example for the surface urban heat island over the New York urban cluster. So this is the urban heat island based on satellite-derived land surface temperature. Now, because of the variability in the local urban effect, that is also related to how populations are distributed within cities. And particularly in the US, we find that in over 90% of cases, poorer neighborhoods within cities tend to be warmer than richer neighborhoods. Similarly, neighborhoods with more non-white populations tend to be warmer than neighborhoods with predominantly white populations. However, one of the issues with a lot of these studies, and this is an issue broadly in large-scale studies of urban climate, is that we have to rely on land surface temperature for a lot of these analyses, partly because we don't have high-density air temperature measurements within cities. But there are many issues with land surface temperature when it comes to trying to understand actual potential for heat exposure. Particularly for urban areas, what the satellites are viewing can frequently be occluded by walls, roofs, etc., which is not relevant to what a pedestrian might feel when they're on the ground. Even if you have the actual radiative skin temperature of the ground, that's not what you're feeling because you're not touching the ground under most conditions using your bare skin. And the air temperature and the land surface temperature also tends to have different urban signals. So here, these are results for the diurnal variation of the canopy, the surface or land surface temperature-based urban heat island and the canopy or air temperature-based urban heat island for over 500 cities in Europe. And you can see that the diurnality is different. So the surface urban heat island tends to have a higher value during daytime. The canopy urban heat island has a higher value during nighttime. And regardless of the time of the day, the surface urban heat island tends to be higher. This is also true when you're looking at distributions of temperature, air versus surface temperature. Generally, in addition to the offset, surface temperature tends to have like wider tails. So if you're using the 95th or 98th percentile to define heat waves, land surface temperature is going to give you very different results than what air temperature is going to give you. The problem is because land surface temperature is used so much in the literature as well, it is very common to talk about land surface temperature changes and differences within cities, and examples from the New York Times and BBC. So do these two neighborhoods have a 20-degree Fahrenheit difference? Well, yes, in terms of land surface temperature, but not necessarily in terms of actual potential for human impacts. Another issue to consider, and that's been not considered as much, is that we know that urban areas tend to be drier. This is known as the urban dry island effect. And we know that humidity also impacts heat stress. So what is the combined impact of temperature and humidity on potential for urban heat stress? So for that, I'm going to talk about a few different studies where we looked at this urban humidity feedback to heat stress. The first study was done using crowdsourced weather stations. We had over 50,000 citizen weather stations over Europe for the July 2019 heatwave period, and we kind of combined the urban warming and drying effect to examine what that meant for different variables within urban areas. One of the analyses was looking at the spatial variability of the different variables within cities. So for this, we defined these regions of increasing warming from like the first decile up to the 10th decile of land surface temperature, and then looked at how the other variables varied in these same regions. So here's what we found. So land surface temperature, of course, increases as you go from like the background to the 10th decile. Air temperature also increases, but by much less than land surface temperature. Relative humidity shows the opposite case, like in the warmest parts of the cities tend to be the driest. This is true both for absolute humidity and also for relative humidity, just because it's a function of air temperature. And then finally, for heat index, which combines temperature and humidity, we see that in most cases, there's not a huge difference. Like if this is not opaque, that means it's not statistically significantly different from the background. So only in like the inner cores, you see a slightly higher heat index than in the background. So we also then wanted to see what this meant for the disparities in heat exposure we saw based on surface urban heat island. We did not have citizen weather station data at these kinds of resolution scales for the US. So instead, we used 1 kilometer simulations over the CONUS and then aggregated the results into census tracts by city. So here what I'm showing is the distribution of the slopes of the linear regression between different variables and income, and each point is one of 482 urban clusters. So regardless of the variable chosen, you see a negative association, which means that as the neighborhood gets richer, the temperature is lower. So there is an income-based disparity. But if you look at the sensitivities, this is the median sensitivity, land surface temperature shows a higher sensitivity than air temperature, which shows a slightly higher sensitivity than humidity, heat index, and then there is humidex. One thing to note is, this is skin temperature from the model, and this is land surface temperature. I'm not going to go into the difference here for that. So these were all based on uncoupled simulations, which have their own issues. And so we also did a separate study where we had ensembles of coupled simulations over the Great Lakes region, and we aggregated these results into 77 community areas within Chicago to try to. We looked at a few different questions, but the one I'm going to focus on here is the coastal gradient of heat. So it is kind of well known that during daytime, because of the lake breeze or sea breeze, you have a gradient with lower temperatures nearer to the shore and higher values as you move inland. But if you look at the different variables, so skin temperature shows the strongest gradient, followed by air temperature, then you have wet bulb globe temperature, then you have wet bulb temperature. A lot of people have covered wet bulb temperature. I'm going to get back to it later. But wet bulb globe temperature is the ISO standard for occupational heat stress, and that includes temperature, humidity, radiation, and wind. And how strong this coastal gradient is a function of how strong the metric itself is to the humidity. Because because of the lake breeze, you also have more humidity nearer to the shore and less humidity inland. And that kind of brings me to kind of this moist heat stress metric issue. I talked about a few different heat stress metrics here, heat index, humidex, wet bulb temperature, wet bulb globe temperature. But if you then compare some of the perturbations to heat indices for different land use, land cover changes, you don't necessarily get the same direction of effects. So this is from a different study currently under review where we are using convection permitting and urban resolving simulations over the US. These are results based on 1,600 urban clusters over the US. So what is interesting here is that we're looking at maximum heat index change due to urbanization and irrigation. So for urbanization, in most cases, you see a decrease in heat stress, moist heat stress, wet bulb temperature, wet bulb globe temperature, humidex, but for heat index, you see an increase. For irrigation, on the other hand, only for wet bulb temperature do you see an increase. For everything else, you see a decrease. So, and this is also true for when we looked at the same results from the observational paper. So when you look at the wet bulb temperature distribution within cities, there's hardly any difference as you move to different deciles. And wet bulb temperature is very commonly used in the earth sciences as a heat stress index, and you may have seen many posters, many talks about it. One thing to note is that wet bulb temperature is interesting because it's a thermodynamic variable. You can analytically dissect it. You can link it to physical mechanisms in analytical frameworks. But it is not a heat stress metric under most conditions because the human body is not a wet bulb thermometer. And the assumptions made to get critical adaptability limits of heat stress based on wet bulb temperature are very idealistic, like imagining a spherical cow kind of situation. And if you look at the epidemiological literature, there are very few studies which use wet bulb temperature as an actual metric. So this is, this looks really bad, but here they compared multiple heat stress metrics and their ability to kind of predict physiological thermal strain. And wet bulb temperature is kind of at the bottom, while wet bulb globe temperature is right at the top. One of the arguments made for wet bulb temperature is because it is one of the components of wet bulb globe temperature, it's still useful to try to understand it. Well, it depends on the research question being asked. So from that same study, so when you look at the wet bulb globe temperature change due to irrigation, it shows a decrease, but wet bulb temperature shows an increase. And this is true not just overall, but by climate zones for pretty much all US urban areas. For urbanization, on the other hand, both show the similar direction of change at least. So yeah, summarizing, well, first, humidity has a negative feedback on urban heat stress, and we shouldn't use quantitative estimates of land surface temperature to talk about public health impacts of urbanization. And we should be very careful about using wet bulb temperature directly as a heat stress metric and as the primary metric in studies, because if you use a different metric, you might get a very different result. Thank you for the chance to be here, for all the collaborators. It's a bunch of references to the papers I talked about.
We do have time for a question if there's.
TC, very nice talk. So I wonder, we talk about the urban environment. We talked yesterday, for example, a lot of talk about indoor heat. So how would these different wet bulb globe temperature probably is not relevant for indoor. How would you suggest what to use?
Yeah, so I think there's been, at least from the climate community, there's been always a focus on outdoor exposure. And the problem is, especially if you look at urban environments, people are not outdoor during the warmest time of the day usually. They're not even living where they are in the census tract data. They're probably working. So if you're like a blue-collar worker versus a white-collar worker, you have very different work environments. So I think we need to incorporate a lot more information about air conditioning penetration, what kind of insulation you have for houses, mobility data to really understand how people are actually getting exposed. Because on the climate side, we are only focused on the hazard. We don't know the exposure, we don't know the vulnerability. So I think we need to really focus on those aspects.
I have a question for the heat stress. I say for richer neighborhoods, it's usually cooler. Is it, so I'm guessing for the model that you're using, it's more like outdoor temperature, or it's, so I'm guessing, is that because of canopy cover or any other reasons for
the urban area to be cooler?
Mm-hmm.
So even if you look at the observational study from Europe, we do find, only for heat index do we find an actual positive daytime maximum urban heat stress island. For the other variables, we find almost close to zero or it's lower. One thing to note is the urban heat island originally came from nighttime observations showing warmer values. So it is primarily a nighttime phenomenon. A lot of the reasons we think urban heat island is higher during daytime now is because of the satellite data, which shows higher values during daytime. So I don't necessarily think that it's wrong that the heat stress island can actually be negative during daytime in urban areas. But again, for exposure, we need to focus on not just hazard, but many other factors to really understand how people are being exposed and responding to environmental conditions.
Thank you.